All right, so I did actually get a request to go over the discussion boards for Organic 1. So give me a minute to load those questions. So it's synthesis with alcohols and reactions of alcohols and alkyl halides. And these are the discussion boards for Organic 1. Come on. So we'll start with reactions of alcohols and alkyl halides, and you've got the reagent. It wants to know if it's stereospecific, and if no, how do you make it? So a lot of the reagents we work with converting alcohols and alkyl halides, these are going to kind of depend, their stereospecificity depends on the reagents we're working with. Now, from a practical standpoint, these stereospecific reagents can be pretty expensive and pretty hard to work with. So it's important to know when we do and don't need stereospecificity. So something like PBr3, this is not a particularly air-stable compound, but something like sodium chloride, you've got that on your table. Thionyl chloride readily reacts with water. Phosphonyl chloride readily reacts with water. KCN does not. And then we have TC, tolusyl chloride, plus KCN. So, sorry, I'm making sure that the video actually sees all of that. Yep. So in terms of stereospecificity, this is just something that you're going to have to memorize. These are in the notes. I make you memorize them because these are pretty common reagents, at least in organic textbooks and organic courses. So PBr3 here, yes. This is stereospecific. So if we have an alcohol, if it's in the S configuration at the alcohol, we put PBr in there, we're going to end up with the R for the alkyl bromide. Sodium chloride is not inherently stereospecific. It depends on if we're going through an SN1 or SN2 mechanism. So if we have like an alkyl bromide or an alcohol, the sodium chloride can go through either the SN1 or SN2 pathways depending on the reaction conditions. So the way we make it specific is that we try to drive the SN2 pathway, and usually when we're talking about this, we're talking about low dielectric aprotic solvents. And what this will do is drive the SN2 pathway. Now the SN2 pathway itself is inherently stereospecific. We always get inversion. So if we have an R alcohol, it'll flip it to an S chloride. If we have an R bromide, it'll flip it to an S chloride and so forth. Now, other thing is that if we do through the SN1, we produce the carbocation, so we end up getting this like racemic mixture of chlorides. We'll get both R and S. So again, if we want to use the NaCl, it's not inherently stereospecific. We can easily conceive of conditions where it's not stereospecific. But if we want to make it stereospecific, we need to drive the SN2 pathway. Thionyl chloride, very much stereospecific. You have an R alcohol, hit it with thionyl chloride, it'll flip back to the S chloride. PlCO3 is the same. PoCl3, same way. The KCN is not. And your big tip off here should be that there's a TCCl down here plus KCN. KCN, that CN minus, is going to act like the Cl minus. So if we have any type of free anion that's basically displacing a functional group on the alkane, it's not really going to be stereospecific, especially if we have the options between SN1 and SN2. So again, if we want to make it stereospecific, we're going to drive it under the SN2 conditions. This is a low dielectric constant solvent, something like diethyl ether, particularly something that is aprotic. So maybe something like tetrahydrofuran. Now, tolusyl chloride. This is a very special reagent. It works specifically with alcohols. There are debates about the actual mechanism, but the end result is always a stereospecific shift. So the tolusyl complex, big nightmare molecule, it's got sulfur on one end, there's benzene ring, there's nitro group on the other, substitutes off the alcohol. So this chlorine pops off and we end up getting an alcohol, that oxygen on the alcohol forming a sulfur ester. It will always do an inversion of symmetry. So if we want to guarantee that our alcohol, whatever we substitute it with, ends up having an inversion of stereochemistry, tolusyl chloride will be the way to do it. And that's why I say it's the hint for TCN. Another way to make KCN stereospecific, work with tolusyl chloride. Now, the other discussion board I got asked about, I do like this one, synthesis with alcohols. And you're given 3 mass specs, and you're asked to predict the products. And you're starting with the cis 2-methyl cyclohexanol. Now, with this, there are 3 products. From the mass spec, you can infer the first one is elimination. So 2 things to note here. We're running this under acid conditions, so it says HCl in the reaction. We can acid catalyze dehydration of this alcohol to give us the alkene. So in this case, we haven't gotten there yet, but we produce the 1-methyl cyclohexene. But you can see this in the mass spec. That mass spec is actually lighter by 18 AMUs versus the other 2. So that's the tip-off. And it does tell you what product is the elimination product of which is the substitution product. So you've got 2 substitution products, product 2 and 3. So how about these 2? Well, we've got HCl, we've got a Cl minus. It's going to act as a nucleophile. So let's consider the SN1 versus the SN2 pathways, because we can get either one, particularly for a secondary alcohol. Tertiary, most likely what we're going to go through is an SN2 mechanism, SN1 mechanism, because it's so big and stabilized. Something like a primary, we can definitely probably going to favor the SN1. But here we got a nice secondary carbon. So if we go through the SN1 mechanism, the first step here is to create the carbocation. So we're going to protonate the alcohol, OH group's going to pop off. And the problem is that we've got a secondary carbocation here, and we can get a hydride shift. And when we do the hydride shift, we end up putting the carbocation on the tertiary carbon. So this is the more stable complex. And when our chlorine attacks, we'll get chlorine attachment on the same carbon as the methyl group. Now you can see, looking left and right, clockwise and counterclockwise, it's the same functional group, so there's no chirality here. So we end up getting the 1-chloro, 1-methyl, cyclohexane. So there's only one product you can form by SN1, and that's because of this carbocation rearrangement. Now for the SN2, SN2s are inherently stereospecific. So for an SN2 mechanism, we always get inversion of symmetry. And we don't produce the carbocation. So we end up getting the trans 1-chloro, 2-methyl, cyclohexane. So in this problem, it is impossible to generate the cis chloro-methyl complex. And the reason being is that in order to do this, we would have to go through an SN1 pathway. And yes, the SN pathway would give us a carbocation. Because it's carbocation, we get both the cis and the transversions. But here's the thing. We have a methyl group. So you would be correct. If I got rid of the methyl group and did the substitution, I would have both the cis and the trans. But again, there's nothing cis or trans to be relative. There's nothing here to be cis or trans relative to. So because of this methyl group, we're going to end up getting rearrangement through an SN1 pathway, and it's going to end up being only one pathway for SN2. So those are the 2 discussion boards right now for Organic 1. That's really about all I had in terms of questions. So if you got any questions, I got the chat open. I'm trying to catch up on conversations right now. But again, post any questions to the discussion board, and I'm here to answer any questions you might have. Oh, I actually got a question. Just one organic packet, page 13. The third census I get why it turns out to be an E1 reaction, having trouble picturing how the bonds are arranged to get the end product. So let me bring up that packet. Man, some of these packets are long. Okay. Third synthesis. So this is the one with this compound. Do let me know if this isn't matching up on your end in terms of the problem. Like there's just sometimes there's page formatting shifts. So if we do this under acid catalyzed conditions, most likely what we're producing is the SN1 pathway. So our first product, or our first step in the reaction, is to generate the carbocation. We are going to get a hydride shift. Oh wait, sorry, drew it wrong. Drew it wrong again. So we got this primary carbocation. Now again, preferably with this primary alcohol, we would like to go through the SN2 pathway, but we're underneath highly acidic conditions in terms of this product. So this carbocation is going to undergo a hydride shift, and we're going to end up producing this carbocation. Now you can get multiple hydride shifts, so this is not to say that it's not possible to get this thing to move further and further down the molecule. The hard reality though is that in order for that to happen, there's an activation barrier. So typically we only see a shift to the adjacent carbons. If we were running at like super high temperatures, yeah, we could probably get the carbocation moving its way along the whole molecule. But for simplicity, we can either get a hydride or a carbon shift, but we can't get it multiple times. So now we need to undergo the elimination. The elimination here is going to follow Zaitse's rule. So I don't understand why that wouldn't just be a hydrogen shift. Okay, I think I see your confusion. Yeah, I'm a little confused on this key too. Because what they've got drawn here is a carbon shift. And that can also occur. So you can get this carbon methyl group moving over, and you would get this, and then the elimination by Zaitse's rule is going to put the double bond here, but you got to do both the cis and trans conformations. But I'm also wondering if it's much more likely you also just have the hydride shift as well. So the hydride shift is kinetically faster. And so my guess is that actually with this key, that answer is incorrect. Most likely what you have is this carbocation, and then you're going to get elimination. To this product. Because that will give you a tertiary carbon, but doing the methyl shift only gives you a secondary hydrogen. Now that said, it is relatively more stable, but the hydrogen kinetically is faster. So my guess is like that's just a mistake in the key. Yeah, not sure why that is what it is. I would probably actually go with that product. Page 15, why is the final product in SN2 where the notice the POCl3 impurity come and make an E product? Let's take a look. So PLCl3 is always symmetry inversion. So the only thing that's going to change here is the alcohol. The POCl3 shouldn't react with anything else. So our seal here is going to remain untouched. And the POCl3 always undergoes an inversion mechanism, so that's what SN2 is inversion mechanism. So let me bring up the notes and see what the notes say. But I agree with the key, like the key's correct. Huh. That's weird. I don't think the notes are correct in that regard. I'll take a look at it. I know PLCl3 doesn't show up on the exam, if that makes you feel better. But everything I read said PLCl3 is a substitution reaction, not an elimination reaction. This may be another one where people debate it. Well, that's not particularly helpful. So the notes say they're used for dehydration, and then I'm finding other sources online that are saying it's also used for dehydration, but I'm also seeing some substitution reactions as well. So I'll look into it. Yeah, I'm seeing it too, and like, notes claim it's for elimination, and that mechanism makes a ton of sense. He may just be wrong. That's a fairly new compound I've had to learn how to work with. Yeah, it probably is meant to be the elimination product. It's a good thing to correct on the key. Again, I can assure you it's not on the exam. I know that, because your book doesn't like to talk about it. question 8 from the Chem 1 test 3 homework. Write the structure formula of trans-4-tert-butyl-cyclohexanol. So start with the base. It's a cyclohexane. It's an all, so our alcohol here is going to occupy one position. And I know there's a stereochemistry, so I'll worry about the stereochemistry in just a minute. Now it's 4. So we have 1, 2, 3, 4. We have a tert butanol, and we want them to be trans. So this is really easy to do with this line bond drawing instead of the boat conformation. So to be trans, one's going to be wedge, one's going to be dash. So this is your trans 4-tert-butyl cyclohexanol. And I can turn the camera around so you can see it. So in terms of drawing it, two, three. That's correct. Well, sticky notes to take notes. You're welcome. Other questions? Your exam is, well, I think your homework's due tonight, and then your exam is due Sunday at midnight. Now, don't forget with the homework, it's not due like you started at midnight. It will lock you out if you don't show up in time. So if you show up at like 11:30 to take the exam, it's going to lock you out because you don't have enough time to take the exam. So make sure you show up at least at 10 o'clock, especially if DSS extensions, make sure you show up an extra hour early, just in case. Page 18 for synthesis. So OH is one of those debatable ones. So there's two things that happen with OH. On the one hand, it is a good, strong base, so that would favor elimination. But it's also a tiny base, which means it favors substitution. So we kind of use OH as a cutoff. So with OH, that's the last time we see substitution. In reality, you would probably get an elimination product with this as well. Now, particularly, I think it's got the THF here. It's kind of implying that you're going through some type of type 2 mechanism, so SN2 or E2. So if you were given an exam, you wouldn't be given anything that ambiguous. But OH minus really does kind of straddle that line of basic enough to do elimination, but small enough to kinetically favor substitution. And this is why if we wanted to guarantee elimination, we would go with something like tert butoxide or something like the sodium azide that's beneath the NH2 minus, because they are so basic and they are so aggressive that they're more likely to do elimination. But yeah, OH minus I would say is kind of one of those cutoffs. It's the last time we see substitution. Substitution will probably be the predominant product, but we're definitely going to see some eliminations in there. Can you also go over question 73 from the same homework? What is the major product of the reaction shown? Select the best answer. So, actually, you're probably just making it way too hard. So we're going to get substitution here. And this is the joy of Fisher projections. So our sodium cyanide and DMSO should undergo a substitution reaction, but it's going to be a substitution reaction in terms of an SN2. So we're going to get symmetry inversion. So the substitution here is going to occur at the bromine, and whenever we invert symmetry in a Fisher projection, all we do is we swap left to right. So the answer here, and watch this be wrong, is that we just get the HC, we get the CN on the opposite side of the bromine. So for me, that's answer A. What? Huh, because I picked the wrong one. It's actually answer B of mine. Yeah. So this is the nice thing about Fisher projections, especially if we know we're going through an SN2 mechanism. The inversion occurs, we flip right, left, right, so we get the substitution, and then to invert the symmetry, we just swap them left, right. Yeah, a nice simple problem. Yeah, you're welcome. Anytime we can work in the Fisher projection, it's a lot easier. Page 24. All right. Oh, this is a good flashback to stuff from test one. This is a good packet. All right, so we got a series of potential products here. And based on the carbon 13 NMR, what did you make? And you've got 4 peaks with a 2 to 2 to 1 to 2 ratio. So first thing we need to make sure if our molecule's got 4 peaks. So we're looking for a symmetry here. So we've got 1, 2, 3, 4. That one checks out. This one has 1, 2, 3, 4, 5, 6, 7. That doesn't check out. This has 1, 2, 3, 4. So this one checks out. And this one has 1, 2, 3, 4, 5, 6, 7. So this one doesn't check out. So now we're down to the last 2. Now the question is, do they appear in the correct ratios? So here we've got 2 to 2 to 2 to 1, 2 to 2 to 2 to 1. So the ratios still check out. Now we actually have to start looking at chemical shifts. And for this, we'd want to go to the worksheets, our NMR data tables. So I'm feeling kind of lazy. I'm just going to Google an NMR data table. Come on, where are you? So in terms of what we would consider an ester or something like that, so I've got a data table up here from Michigan State University chemistry. They say an oxygen-carbon shift, there's something that has this structure, is looking at a chemical shift of, where are you? 50 to 100 ppm. Here, these alkenes, we're looking at a chemical shift of 170 to 130. And these both contain methyl groups. These are chemical shifts of like 20 to 50. So if you look at the actual data table that it provides, there's a chemical shift of 131, 125.7. That's outside the range for this one, so it's looking like that's the carbon 13 NMR. But you are correct, it doesn't show up in the key. It's probably it was meant to show up in the key. I'm curious. There's a way I can cheat to see if I actually wrote down what the answer was in the key. Ah, that was mean. But yeah, based off the carbon 13 NMR, I would say it's the diene, the one that has the two alkenes in it, because of those 131 and 125 chemical shifts. Because that 27.9, 16.5, that's these. And same thing's true here. These are also going to be fairly well upfield because they are representative of like alkanes. Other questions out there? Excuse me. You're welcome. All right, so that kind of seems to be the end of the questions there. So let's go ahead and head out for today. Again, homework's due tonight. The exams are due Sunday. Make sure you start them with plenty of time to start the exams. I will try to be available via email. But yeah, it's the weekend. So anyway, thanks for those of you who were able to come today, and I will see y'all next week.